Hello friends, greetings of the day. Today we are learning a special category of problems corresponding to dummy variable. Here dummy variable occurs as a dependent variable. As for example, if a person holds a credit card or debit card depends upon his income, his work experience, etc. So, the answer is either yes or no, only two categories, so it is a dummy dependent variable. Our usual models will not be applied here due to the special nature of this problem. So, here we will study what is known as linear probability model, logit model, probit model, etc. So, let us now listen to the lectures.
In today's session, we will discuss regression analysis for dummy dependent variable. In all our studies so far pertaining to regression analysis, the dependent variable or regressed is a quantitative variable, whereas the explanatory variables can be quantitative or qualitative or a mixture of both quantitative and qualitative. Since dependent variable is under the effect of all other variables which are independent or exogenous, it is also called response variable. In practical applications, we do not always have a dependent variable which is quantitative in nature. That is, the dependent or response variable can be qualitative in nature. To understand this, let us take two illustrations. Number 1, yi equal to alpha plus beta 1 xi plus beta 2 di plus ui. Here, y equal to labor force participation and yi equal to 1 if a person is in the labor force and 0 otherwise. X equal to average wage rate, di equal to 1 if the person is male and 0 otherwise. U equal to disturbance term. Here, response variable y is a dummy dependent variable with two categories. X is quantitative variable and di is dummy independent variable. Number 2, yi equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus delta di plus ui. Here, y means whether a person is having debit card or not. yi equal to 1 if the person has a debit card, 0 otherwise. x1 equal to monthly income of the person, x2 equal to years of service of the person, di equal to 1 if the person is educated and 0 otherwise. Same, u equal to disturbance term. Here also we have one dummy dependent variable, two independent explanatory variables and one independent dummy variable. We want to study now the case where the dependent variable is a qualitative variable. Such study is also known as study of qualitative response regression models. Looking to the nature of the problem, it is evident that its study needs a separate treatment compared to our earlier studies. If there are only two categories of dummy dependent variable, that is yes or no or 0 and 1, it is called binary or dichotomous variable. There can also be more categories with respect to persons belonging to political party A or party B or party C, which is called trichotomous, and in this way for many categories it is called polychotomous multiple category. We want to study here binary response regression models. There are certain models under these studies like number 1, linear probability model denoted by LPM, number 2, logit model, number 3, probit model and number 4, tobit model, etc. Linear probability model denoted by LPM. We want to discuss here two variables model with y as dummy dependent variable with two categories and one explanatory independent variable. Some more illustration for binary response variable can be given as number 1, y equal to 1 if a certain drug is effective and y equal to 0 if it is not effective. Y equal to 1 if a family has disability insurance and 0 if the family does not have insurance. Y equal to 1 if a company wants to declare bonus shares, etc. and 0 if not. Let us consider here the model yi equal to beta 1 plus beta 2 xi plus ui. We denote it as equation number 1, where I equal to 1 to up to n. Here yi equal to 1 if the family owns a house, 0 if it does not. X equal to family annual income, U equal to disturbance term. Here the described model is called linear probability model LPM. We define Pi equal to probability of Yi equal to 1, which means probability that family owns a house. Probability of success means probability that event will occur. Then 1 minus Pi equal to probability of Yi equal to 0, which means probability that family does not own a house. Probability of failure means probability that event will not occur. The probability distributions variable Yi has shown here. We assume that expected Ui equal to 0, then from equation 1, expected Yi given Xi equal to beta 1 plus beta 2 Xi, we denote it as equation number 2. Now, expected Yi equal to 0 multiplied by 1 minus Pi plus 1 multiplied by Pi, which is equal to Pi, we denote it as equation number 3. Hence, from equation 2 and 3 we get expected Yi given Xi equal to beta 1 plus beta 2 Xi equal to Pi, we denote it as equation number 4. Since 0 less than or equal to Pi less than or equal to 1, we get 0 less than or equal to expected Yi given Xi less than or equal to 1, we denote it as equation number 5. Estimation in LPM. While estimating LPM, there are certain problems which can be summarized briefly as: number 1, non-normality of the disturbance term. From the model Yi equal to beta 1 plus beta 2 Xi plus Ui equal to Yi minus beta 1 minus beta 2 Xi. Hence, when Yi equal to 1, Ui equal to 1 minus beta 1 minus beta 2 Xi, and when Yi equal to 0, Ui equal to minus beta 1 minus beta 2 Xi. Thus, Ui takes only two values as shown. Due to this, it is incorrect to assume normality for Ui. However, for large samples, normality assumptions can be considered to be valid. In fact, for estimation purpose, normality assumption is not needed. So, OLS estimators will be unbiased, and in large samples, the inference of LPM will follow the usual OLS procedures under the normality assumptions. Number 2, heteroscedastic variance of Ui. For LPM, we assume that expected Ui equal to 0 and also expected Ui Uj equal to 0. Here, I is not equal to j. For all I and j, we have values 1 to up to n. That means there is no serial correlation between the disturbances. We obtain probability distribution of Ui, which is shown here. Since expected Ui equal to 0, variance of Ui equal to expected Ui square, which is equal to minus beta 1 minus beta 2 Xi whole square multiplied by 1 minus Pi plus 1 minus beta 1 minus beta 2 Xi multiplied by Pi. Put Pi equal to beta 1 plus beta 2 Xi, then simplification gives variance of Ui equal to beta 1 plus beta 2 Xi multiplied by 1 minus beta 1 minus beta 2 Xi, which is equal to Pi multiplied by 1 minus Pi. We denote it as equation number 6, and simplification we get expected Yi given Xi multiplied by 1 minus expected Yi given Xi. We denote it as equation number 7. Thus, there is heteroscedasticity. In the presence of heteroscedasticity, OLS estimators are unbiased but not efficient. This can be dealt with by the usual remedial measures to overcome the problem of heteroscedasticity. Method: let under root of Wi equal to under root of Pi multiplied by 1 minus Pi. We denote it as equation number 8. Then we divide both sides of equation 1 by under root of Wi, so that we get Yi upon under root of Wi, which is equal to beta 1 upon under root of Wi plus beta 2 multiplied by Xi upon under root of Wi plus Ui upon under root of Wi. We denote it as equation number 9. It can be easily checked that even though original model has heteroscedasticity, the transform model has homoscedasticity. We have to estimate Wi to operate on the model. Since expected yi given xi equal to pi and wi equal to pi multiplied by 1 minus pi, we get wi cap equal to pi cap multiplied by 1 minus pi cap, which is equal to expected yi cap given xi multiplied by 1 minus expected yi cap given xi, which is equal to yi cap. We denote it as equation number 10. We have two-stage procedure to operate on the model. Stage number 1. As usual, run the regression of yi on xi and find OLS estimates and hence find yi cap. Hence, wi cap equal to yi cap multiplied by 1 minus yi cap. We denote it as equation number 11. Step 2. Run the regression of the transform model given in equation 9 and find the estimators. Number 3. Non-fulfillment of the condition 0 less than or equal to expected yi given xi less than or equal to 1. Theoretically, we accept that expected value of yi given xi lies between 0 and 1. However, while computing yi may not follow such a rule. This becomes a crucial problem with LPM. There are two ways for finding out whether yi cap lies between 0 and 1 or not. Number 1. Estimate LPM by usual OLS method and find yi cap. Judge about the values obtained for yi cap. If some values are negative, take them as 0. Similarly, if some values are greater than 1, take them as 1. This is the usual practical approach for dealing with the problem. Number 2. Some special methods are to be devised to check this point to ascertain that yi cap lies between 0 and 1. Note: Number 1. To overcome this difficulty, further studies for logit and probit models can be done. Number 2. It is not proper to conclude about the correctness of the LPM model based upon the value of R square. In most of the cases, R square lies between 0.2 and 0.6. It is only when the scatter plot shows a cluster of points that appears very near in a line. In such cases, R square will be in excess of 0.8. Hence, use of R square as a summary statistic should be avoided with qualitative dependent variables. Logit model. Now we consider further modification to LPM model so that the drawbacks or limitations of the model can be overcome by considering some new way of presentations. This is achieved by what is called logit model. We shall continue our earlier illustration with the model yi equal to beta 1 plus beta 2 xi plus ui, where I equal to 1 to up to n, and we denote it as equation number 1, where x equal to family income, yi equal to 1 if the family owns a house or 0 otherwise. As done in LPM, we assume expected ui equal to 0 for all I equal to 1 to up to n, so that expected yi given xi equal to beta 1 plus beta 2 xi, we denote it as equation number 2. We set pi equal to probability that the family owns a house. Therefore, pi equal to expected yi equal to 1 given xi equal to beta 1 plus beta 2 xi. We denote it as equation number 3. Let us define pi equal to 1 upon 1 plus exponential minus beta 1 minus beta 2 xi. We denote it as equation number 4. If we write zi equal to beta 1 plus beta 2 xi, we denote it as equation number 5, then we get pi equal to 1 upon 1 plus exponential minus zi. Hence, pi equal to exponential zi divided by 1 plus exponential zi. We denote it as equation number 6. Equation 6 is called CDF of logistic distribution, that is logistic distribution function. Note that as zi ranges from minus infinity to plus infinity, pi range between 0 and 1 and pi is non-linearly related to zi and hence to xi. This partially solves the problem found in LPM. However, we have created an estimation problem because pi is non-linear not only in xi but also in the beta coefficients. This means that we cannot use OLS estimation procedure to estimate the parameters. To solve this problem, let us consider the ratio. Probability that family owns a house divided by probability that family does not own a house, which is equal to pi upon 1 minus pi, which is equal to 1 plus exponential zi upon 1 plus exponential minus zi, which is equal to exponential zi. We denote it as equation number 7. This ratio is called odds ratio, ratio of probability of success to ratio of probability of failure. For example, if Pi equal to 0.6, odd ratio equal to 1.5, which means that odds are 3 to 2 in favor of the family owning a house. Let us take logarithm to natural base for this ratio and denote it by Li. Then Li equal to ln of Pi upon 1 minus Pi, which is equal to Zi, which is equal to beta 1 plus beta 2 xi. We denote it as equation number 8. This last equation Li equal to beta 1 plus beta 2 xi shows that the log of the odds ratio is not only linear in x, but it is also linear in parameters. L is called logit, and hence we have what is called logit model given by Li equal to ln of Pi upon 1 minus Pi, which is equal to Zi, which is equal to beta 1 plus beta 2 xi plus ui. We denote it as equation number 9. Some features of logit model. Number 1. As p goes from 0 to 1, that means as z varies from minus infinity to plus infinity, the logit L goes from minus infinity to plus infinity. Thus, even though probabilities lie between 0 and 1, the logits are not so bounded. Number 2. LPM assumes that Pi is linearly related to xi. The logit model assumes that log of odds ratio is linearly related to xi. Beta 2 is the slope indicating change in L for a unit change in x. This means how is the log of odds ratio in the favor of owning a house as income changed by a unit. Beta 1 is the intercept term for logit model. L is linear in x, but the probability by themselves are not. Number 5. We have included a single explanatory independent variable x, but we can add many such explanatory variables as regressors, and odds ratio and hence L can be defined accordingly. How to estimate logit model? Case number 1. Data at the individual level. If we have data on the individual families, we cannot use equation 8 due to the nature of the data. Yi equal to 1, that means Pi equal to 1, which gives Li equal to ln 1 upon 0 if family owns a house. Yi equal to 0, which means Pi equal to 0, which gives Li equal to ln of 0 upon 1 if family does not own a house. Both of these are meaningless. Here we should use maximum likelihood estimator, which is called MLE. This is achieved by using AML method. First we write likelihood equation, then logarithm of likelihood equation lean the parameters beta 1, beta 2. Necessary condition is delta L upon delta beta I equal to 0, and sufficient condition is delta square L upon delta beta I square less than 0, where I equal to 1 and 2. We get very complicated form and we can solve it by adopting usual methods for obtaining MLE. Some software packages like Microfit, eViews, LimDep, Shazam, PCGive, Stata and Minitab have built-in routines to estimate the logit model at the individual level. We can use them to solve the problem. Case number 2. Grouped or replicated data. There can be data for several families for our problem stated earlier, which are grouped or replicated according to the number of families owning a house at each income level. Thus, corresponding to each income level xi, there are Ni families and Ni among them are those who own their house. Hence, we can compute the relative frequency which measures the probability using frequency definition of probability. Hence, for our above stated logit model, ln equal to ln of Pi upon 1 minus Pi equal to Zi equal to beta 1 plus beta 2 xi plus ui. We denote it as equation number 9. We can have Pi equal to Ni upon capital Ni, which estimates Pi. Thus, Pi cap equal to Pi, which is equal to Ni upon capital Ni. We denote it as equation number 10. Hence, Li equal to ln Pi cap upon 1 minus Pi cap equal to Zi, which is equal to beta 1 plus beta 2 xi plus ui. We denote it as equation number 11. We have to run regression based upon equation number 11 and find estimators of beta 1 and beta 2. Hence, Li cap equal to ln of Pi cap upon 1 minus Pi cap, which is equal to beta 1 cap plus beta 2 cap xi. We denote it as equation number 12, where beta 1 cap and beta 2 cap are the estimates of beta 1 and beta 2. Can we run OLS regression? Answer is no. Why? The reason is that there is heteroscedasticity of disturbances. Let us examine this first before running regression. Under normality assumption, if Ni is fairly large, Ui follows normal distribution with mean 0 and variance 1 upon Ni Pi multiplied by 1 minus Pi. This shows that there is heteroscedasticity. We can write sigma cap square equal to 1 upon Ni Pi cap multiplied by 1 minus Pi cap, which is equal to 1 upon under root of Wi, where Wi equal to Ni Pi cap multiplied by 1 minus Pi cap, which is equal to Ni Pi multiplied by 1 minus Pi. We can divide logit model by 1 upon root Wi so that root Wi Li equal to beta 1 root Wi plus beta 2 multiplied by root Wi multiplied by xi plus root Wi multiplied by ui. Thus, Li star equal to beta 1 star plus beta 2 star xi plus vi star, where Li star equal to root Wi Li, beta 1 star equal to beta 1 multiplied by root Wi, beta 2 star equal to beta 2 multiplied by root Wi, and vi star equal to root Wi multiplied by ui. Check that expected vi star equal to 0 and variance of vi star equal to sigma square. Hence, the transform model has heteroscedasticity. Even though originally there is heteroscedasticity, we follow the estimation procedure as: number 1. For each income level xi, compute the probability of owning a house as Pi equal to Pi cap equal to Ni upon capital Ni. Number 2. For each xi, obtain the logit as Li cap equal to ln of Pi cap upon 1 minus Pi cap. Number 3. Obtain Wi equal to Ni Pi cap multiplied by 1 minus Pi cap. Number 4. Find Li star equal to under root of Wi multiplied by Li and beta 1 star equal to beta 1 multiplied by root Wi, beta 2 star equal to beta 2 multiplied by root Wi. Number 5. Run the regression for the transform data Li star equal to beta 1 star plus beta 2 star xi plus ui star and obtain OLSE of beta 1 star and beta 2 star. Note that number 1. This procedure is valid if the sample is of reasonably large size. Number 2. We can obtain confidence intervals and do testing problem as usual. Number 3. We can get inference about odds ratio for interpretation purpose. Now, let us understand number 4, which is probit model. In logit model, we have used cumulative logistic function. This is not the only CDF that one can use. In some applications, the normal CDF is found to be useful. The estimating model that emerges from the normal CDF is popularly known as probit model. It is also known as normit model. To understand about this model, we considered further our house ownership example. Whether ith family own a house or not depends upon utility index II, also called latent variable. Thus, larger the value of II, greater is the probability of owning a house. We express this index as II equal to beta 1 plus beta 2 xi. We denote it as equation number 1, where xi equal to income of the ith family, as before y equal to 1 if the family owns a house and y equal to 0 otherwise. We assume that there is a threshold level of the index denoted by II star, such that if II greater than II star, the family will own a house, otherwise it will not. II as well as II star are not directly observable, but with the help of normal distribution assumption, we can deal with the problem. Under normality assumption, Pi equal to probability of yi equal to 1 given x equal to probability of II star less than or equal to II, which is equal to probability of Zi less than or equal to beta 1 plus beta 2 xi, which is equal to f of beta 1 plus beta 2 xi. We denote it as equation number 2. Zi is standard normal variate and Fi is its CDF, which is equal to f of II, which is equal to 1 upon root 2 pi integration from minus infinity to I exponentially minus z square upon 2 dz, which is equal to 1 upon root 2 pi integration from minus infinity to beta 1 plus beta 2 xi exponentially minus z square upon 2 dz. We denote it as equation number 3. To obtain information on II, the utility index, as well as on beta 1 and beta 2, we take inverse of relation gives in equation number 2. Thus, II equal to F inverse II, which is equal to F inverse Pi, which is equal to beta 1 plus beta 2 xi. We denote it as equation number 4. Here, F inverse is the inverse of the normal PDF. We can deal with this problem by using tables of normal distribution CDF. Once we obtain II, then for given xi, we can run the regression equation number 4 using OLS method to estimate beta coefficients. This model seems to be mathematically difficult. There are sophisticated statistical packages which are available to solve the problem. It may be noted that both logit and probit models give similar results, and also both are equally popular for application purposes. Note: number 1, an extension of probit model is Tobit model, which is developed by James Tobin. It uses censored data. Hence, it is also called limited dependent variable regression model. Number 2, further studies on these lines are very interesting. For example, Poisson regression model, ordinal logit and probit models, multinomial logit and probit models, duration models, etc. Thank you.